Thank you for introduction. Let me start my presentation. The title is The Current Status of Dance, Dark Matter Action Search with Ring Cavity Experiment. The speaker is Yuka Oshima, a graduate student of the Department of Physics, the University of Tokyo. We proposed an extremely new method to search for axion-like particles with a tabletop experiment, that is, dark matter axion search with ring cavity experiment. Our group called this project for short, DANCE. Now, prototype experiment, DANCE Act 1, is ongoing at the University of Tokyo. First, I will introduce axion and previous researches. We know that dark matter exists in the universe, and we have searched dark matter, especially WIMP, for a long time. However, dark matter is not detected yet, so we need to search dark matter in wider mass range. Now, ultralight dark matter search with laser interferometer, such as gravitational wave detectors, is gathering much attention from many researchers. Axion is hypothetical particle to solve the strong CP problem in QCD. Many kinds of axion-like particles are predicted by superstring theory. Axion-like particles is one of the candidates for dark matter. Many groups proposed various methods of measuring axion-photon coupling, especially by using magnetic field. This figure shows current upper limits from previous researches. Horizontal axis shows axion mass. Vertical axis shows axion-photon coupling constant. The lower is the better sensitivity. CAST, CERN Axion Solar Telescope, and X-ray observation by Chandra Telescope have current upper limits of axion-photon coupling. I'll move on to method section. The principle of DANCE is to measure rotation of linear polarization, not using magnetic field. Axion-photon coupling causes phase velocity difference between left and right-handed photons. In this equation, GA gamma means coupling constant, A0 means axion field, and MA is axion mass. If we assume a linear polarization to be the superposition of left and right-handed photons, like this figure, phase velocity difference of circular polarizations makes linear polarization rotate. We'd like to measure rotation angle of linear polarization caused by axion, if axion is dark matter. If we do not use a cavity, rotation angle is too small to be observed. In a cavity, laser light runs between mirrors many times. Therefore, rotation angle can be amplified with a cavity. In a linear cavity, rotated direction is inverted, so the rotation effect is not accumulated, but cancelled out in a linear cavity. However, a vortiling cavity prevents linear polarization from inverting rotated direction because laser light is reflected twice in a vortiling cavity. This figure shows design sensitivity of DANCE. Red dashed line shows design sensitivity of prototype experiment DANCE Act 1, and pink dashed line shows design sensitivity of the final version of DANCE. You can see that DANCE will improve the current sensitivity by several orders of magnitude compared with the current sensitivity. These sensitivity curves are calculated if only shot noise is in the experiment. Shot noise is quantum noise caused by fluctuations of number of photons detected. So we need to minimize all noises other than shot noise. Here is experimental setup of dance. We use laser source that has the wavelength of 1064 nanometers. Laser light goes through Faraday isolator, EOM, collimators, and an optical fiber. We make a linear polarization with polarizing beam splitter and inject into a ring cavity. Reflected light is used to frequency servo. Transmitted light goes through half-wave plate and second PBS. We can get the signal of action with 2 photodetectors. This is a configuration of frequency servo by PDH technique. We'd like to lock laser frequency to the resonance of a ring cavity in order to obtain the data for a long time. Laser frequency is modulated with EOM, and the signal of reflected light is demodulated with mixer. Feedback signal is returned to the laser piezo actuator. Then we can get a clear PDH signal and we can achieve the feedback control. This is a picture of the whole setups. We made 2 stories of optical tables. On the first floor, we put laser source and EOM. Laser light is lifted to the second floor with an optical fiber, and we put a ring cavity and photodetectors on the second floor. I will explain about experimental results. We measured these quantities to evaluate the performance of a ring cavity. This column shows design values, and this column shows measured values of with P polarization. Almost measured values are consistent with design values. However, measured finesse of 500 is much smaller than design finesse of 3000 due to the loss of light of 0.91%. Designed value of laser input power is 1 watt, but now we are injecting the laser power of 40 milliwatt because we are still adjusting setups. Finesse means the number of round trips. Finesse and input power are important quantities to improve the sensitivity because the sensitivity depends on finesse and input power. I will explain how to get the data. This half-wave plate is fixed to make equal amount of P and S polarization. Then we record a differential power of P and S polarization with a data logger. We use a subtraction circuit in order to remove common noise of P and S polarization and to reduce quantization noise of a data logger. We analyze the data with this equation, then plot the spectrum of rotation angle. The orange solid line is current estimated sensitivity if we observe for a year. We have to improve the current sensitivity by 3 to 5 orders of magnitude to reach the design sensitivity of Dance Act 1, this red dashed line. Finally, discussion section and future plans. Red line is relative intensity noise of incident light, and blue line is the spectrum of rotation angle. They have strong correlation in 0.1 to 10 Hz. So we can say that the current sensitivity is limited by laser intensity noise in low frequency. We found that an optical fiber causes this noise. In 10 to 1 kHz, there is high coherence between feedback signal and rotation angle. feedback signal has information about external noise, so the current sensitivity is limited by external noise, such as seismic or sound or mechanical vibration in 10 to 1 kHz. This is a rough estimation of sensitivity improvement. If we can eliminate all noises other than shot noise, we will improve the sensitivity by 1 to 3 orders of magnitude, and we can achieve this orange dashed line. Furthermore, if we will improve finesse and laser power, we can achieve the design sensitivity of dance act 1, this red dashed line. We have future plans as follows. We'd like to improve finesse by changing to high quality mirrors and improving alignment of mirrors. We will reduce noises. Now we are constructing setups without an optical fiber on the first floor, and we will reduce external vibration by surrounding optical tables with black plates. Then we will inject higher laser input power into a cavity. That's all. Thank you for listening.